Touch isn't a collision, it's a push. Right now, if you press your fingertip against the nearest hard surface, a desk, a phone, a wall, something is pushing back. You can feel it. It's steady and completely taken for granted. But the reason it happens is one of the most beautiful stories in all of physics. And here's the thing, most people, when they first hear the explanation, expect it to make the world feel less real, less solid, less trustworthy. What actually happens is the opposite. The more clearly you see what's going on at the small scale, the more impressed you become that anything holds together at all. The floor beneath you right now is doing something extraordinary. Your chair, if you're sitting in one, is performing a kind of structural feat so consistently that you've stopped noticing. Let's start noticing again. We're going to spend some time today with a simple, stubborn question. Why can't you walk through a wall? Not as a joke, not as a koan, as a serious physics question that deserves a serious answer. And the answer involves electrons, the nature of space, forces we can't see, and a principle of quantum mechanics so fundamental that without it, chemistry and solid matter as we know them wouldn't survive. No drama needed. The real story is already astonishing. Let's begin somewhere familiar. Put your hand flat on a table. Now press down, just a little. You feel resistance. The table pushes back. This is so obvious it barely registers as interesting. But let's slow down and ask, what exactly is doing the pushing? Your first instinct might be to say, the table is hard, and hard things don't let other hard things pass through them. But that answer is circular. It explains hardness with hardness. What we actually want to know is what makes something like that in the first place, all the way down. The answer begins with atoms, but the way atoms actually work is almost certainly different from the picture most of us carry around. The common image, a tiny solar system with a dense nucleus in the middle and electrons orbiting around it like small planets on neat circular tracks, is useful for counting electrons and drawing molecular diagrams. In an important sense, though, it is misleading. Electrons don't orbit the nucleus in crisp little circles. They don't have definite paths at all. What an electron actually is, in the quantum mechanical picture, is something closer to a distributed presence. There's a region of space around the nucleus where the electron is likely to be found. More likely in some places, less likely in others. And that region has a shape and a size, but it doesn't have a sharp edge the way a marble does. Physicists call these regions orbitals. When you have many electrons around many atoms, you end up with these overlapping, fuzzy, probabilistic structures extending out into space. The electron isn't a dot on a track. It's more like a standing wave, a smeared out pattern of likelihood that fills a volume. Now this might sound like the electrons are spread out and vague and therefore harmless. But here's where things get interesting. These distributions of electron probability are not passive. They carry electric charge, and electric charge produces forces. Think about your fingertip again, pressing on that table. Your fingertip is made of atoms. The table is made of atoms. As your finger moves closer to the surface, the outermost electrons of the atoms in your fingertip are coming into the vicinity of the outermost electrons of the atoms in the table's surface. And electrons are negatively charged, so electromagnetism matters immediately. But at very close range, the steep resistance is also shaped by quantum rules that limit how those electron states can be packed together. We'll come back to those quantum rules shortly because they deserve their own careful explanation. For now, the key point is this: the repulsion is real, it is forceful, and it grows with extraordinary speed as the distance between atoms shrinks. But it's more subtle than simple repulsion alone, because at moderate distances atoms don't simply push away from each other, they actually attract. If two atoms are far enough apart, there's a gentle pull between them, partial attractions between opposite charges, shifting distributions, a kind of mutual accommodation that draws them together. This is how molecules form. This is why liquid water is liquid instead of a gas at room temperature. The molecules are attracted to each other enough to stay loosely connected. So you have this interplay. At moderate distances, atoms and molecules are gently drawn toward each other. They want to stay close. But as you push them closer and closer together, the repulsion doesn't just increase, it increases steeply, extraordinarily steeply. The force pushing them apart grows so fast as the distance shrinks that it becomes, for all practical purposes, impossible to overcome with any ordinary amount of force. Physicists describe this with something called the interatomic potential, a curve that shows how the energy between two atoms changes with distance. There's a comfortable sweet spot distance where the atoms would rather sit. Push them closer, and the energy shoots up sharply. Try to merge them entirely, and the energy climbs so fast that you'd need conditions found only in the cores of stars or high-energy particle colliders to continue. The ground under your feet is sitting at that sweet spot right now. Every atom in your chair, every atom in your floor is in a kind of negotiated equilibrium with its neighbors. When you press your hand on a table, you're asking the atoms in your hand to get closer to the atoms in the table than those atoms want to be. And they resist, with a force rooted in electromagnetic interaction, reinforced by quantum mechanical structure, together forming one of the most dependable phenomena in nature. This is what pushback actually means at the atomic level. It is real. It is not a philosophical trick. The table is physically resisting you, and the mechanisms doing the resisting reach all the way down to the fundamental laws of physics. Now stand up for a moment, or imagine standing up, and think about your feet on the floor. Every time you take a step, your foot descends toward the ground and then stops. Not because your foot hits a wall, not because something mechanically blocks it the way a door stopper blocks a door. Your foot stops because the atoms in the sole of your shoe and the atoms in the floor reach that zone of steep repulsion, that region where the force becomes so strong, so rapidly increasing with decreasing distance, that no amount of force your leg muscles can generate will push them closer. Your weight, every kilogram of you, is supported continuously by this repulsion operating between trillions of atoms. The floor is not passively there. It is actively pushing back. It has been pushing back every second you've been standing on it, without pause, without fatigue, without error. Think about what that means for a building. A skyscraper, or even an ordinary house, is held up entirely by this force, transmitted through concrete, steel, glass, and wood, all the way down through the foundation and into bedrock. Every floor supporting its ceiling, every wall bearing its load, every beam resisting compression, all of it, ultimately, is the repulsion between electron distributions passed from atom to atom through the structure of matter. The world is not made of continuous lumps of stuff with no inner structure, but it is as solid as anything needs to be. And the reason is this: the force that keeps atoms from merging is powerful, consistent, and utterly indifferent to outside opinion. It does not take days off. It does not depend on your believing in it. Let's try another thought experiment. Shake someone's hand. When two hands clasp together, you feel warmth, texture, pressure. What you're actually feeling, through the medium of nerve signals in your palm, is the force from the other person's outermost electrons pressing against yours. Their atoms and your atoms are sitting just at the edge of that repulsion zone, close enough to feel, not close enough to merge. The pressure you sense as firmness in a handshake is a distribution of force across millions of contact points between skin cells. And there's something worth pausing on here. Two people, when they shake hands, never achieve what you'd call direct atomic contact in the sense of nuclei touching. What they achieve is an intimate proximity, a negotiated closeness where the repulsion is felt but not overwhelmed. The handshake has a depth to it, measured in fractions of a nanometer, where the forces from each hand's electron distributions meet and respond to each other. You are, in the most literal physical sense, feeling the shape of another person's atoms. This isn't a diminishment of the experience. It doesn't drain the warmth out of human contact. If anything, it's a reminder that the physical world is intricate at every scale, and that the ordinary act of grasping a hand is connecting two quantum mechanical structures in a way that is specific, responsive, and thoroughly real. Now let's sit down and lean against something. Imagine you're in a chair, your back pressed lightly against a wall. The wall does not feel your presence the way a person would, but it responds to it physically. Wherever your body makes contact with the wall, the atoms at the surface of your clothing or skin are interacting with the atoms of the wall's surface. The wall is pushing you outward, your body is pushing back, and the net result is that you stay exactly where you are, supported, positioned, stable. There's a word physicists use here, equilibrium. You are in mechanical equilibrium with the wall. The forces are balanced. You are not accelerating into the wall, and the wall is not accelerating into you. You are both sitting at the bottom of that energy curve, that comfortable distance where everything is settled. Now ask yourself, why doesn't the wall give way? Why doesn't the force of your leaning body push those wall atoms far enough that they begin to slide and collapse? The answer is that the atoms within the wall are also in equilibrium with each other. They're bonded, meaning they're sitting at their own comfortable distances, each pair of atoms held by that same interplay of attraction and repulsion. To move those atoms far enough to break the structure of the wall would require overcoming all of those bonds simultaneously, which takes far more energy than a person leaning against a surface can provide. This is why structural integrity exists at all, why walls stay walls, why floors stay floors, why your own skeleton holds its shape. The bonding between atoms is not fragile. It is a consequence of the same forces we've been tracing all along, applied to a network of atoms in such a way that the whole structure becomes stable against ordinary disturbances. You can lean on a wall all day. It will hold. Now, we've been talking primarily about the electromagnetic force, the push between like-charged electrons. But there's another layer to this story, and it's one of the most remarkable results in all of quantum mechanics. It's called the Pauli Exclusion Principle. Here's the idea, stated as simply as possible. Electrons are what physicists call fermions, a category of particle defined by the fact that no two of them, within the same quantum system, can occupy exactly the same quantum state. Quantum state is a technical term, but you can think of it informally as the complete description of a particle's situation, its energy level, its orientation, its location probability, its spin. Two electrons cannot share all of these properties simultaneously. They have to be in some way distinct. This is not a rule that electrons follow because they're obedient. It comes out of the deepest mathematics of quantum mechanics, from the way the wave functions of identical particles combine. When you try to force two electrons into the same region of space in the same state, the mathematics itself resists it. The probability of that configuration collapses. The practical consequence is that electron distributions resist being compressed into each other. When you push two atoms together, it's not only that the electrons repel each other electromagnetically, the quantum rules of occupation also come into play, making it harder and harder for those distributions to be forced into the same region of space. The Pauli Exclusion Principle reinforces the steepness of that repulsion. It adds a structural backstop on top of the electromagnetic foundation. Think of electromagnetism as the first wall of resistance, and the Pauli principle as the reason that wall gets dramatically steeper the harder you push. One thing worth being clear about: the electron distributions of neighboring atoms do partially overlap, particularly at their edges. Quantum mechanics doesn't draw sharp lines the way classical pictures do. But a partial overlap at the tails is very different from a full merger, and the Pauli Exclusion Principle is one of the key reasons complete merger is so strongly resisted. Together, electromagnetic repulsion and quantum mechanical exclusion, these effects make matter resistant to interpenetration under ordinary conditions. Not just stiff, not just firm, resistant in a way that is woven into the mathematics of how quantum particles behave in space. At this point, you might be wondering, if the forces are so clear, if the rules are so consistent, is it truly impossible for matter to pass through matter, even in principle? This is where we have to be honest and precise, because quantum mechanics doesn't always deal in clean absolutes. There is a phenomenon called quantum tunneling. It refers to the fact that a quantum particle has a non-zero probability of appearing on the other side of a barrier that classical physics says it cannot cross. Electrons tunnel, protons tunnel. Tunneling is responsible for nuclear fusion in the sun, for certain types of radioactive decay, for the operation of tunnel diodes in electronics. It is real and thoroughly verified. So in a strict technical sense, there is a non-zero probability that a quantum particle can cross a barrier without going over it in the classical sense. And if you asked whether this applies in principle to a human being and a wall, the honest answer is yes. In principle, the probability is not exactly zero. But the word non-zero is doing enormous work in that sentence. For a macroscopic object with anything close to the number of particles in a human body, the probability is so vanishingly small that no meaningful distinction exists between it and zero. The universe could cycle through more iterations than we have language to describe, and you would still be waiting. Tunneling matters profoundly for subatomic particles. For people and walls, it simply does not enter the picture. We mention it because honesty requires it, and then we move on. Let's return to something touched on earlier, because it deserves more care. The phrase, empty space. You may have heard that atoms are mostly empty space, that if you scale the nucleus up to the size of a marble, the nearest electrons would be something like a football field away. This is accurate, and it does mean that mass is very sparsely distributed at the atomic scale. Most of the mass lives in nuclei, and nuclei are extraordinarily small. But stopping there gives the wrong impression. It can make matter sound like an airy nothing, mostly gaps, barely present. And that framing, while technically true about where the mass sits, misses something essential about what fills that apparent emptiness. The region around the nucleus, the region that looks like a gap if you're only tracking mass, is not nothing. It is occupied by the electron's probability distribution, a real physical structure that carries charge, fills a volume in a meaningful sense, and interacts with other such structures through genuine forces. When two atoms approach each other, it's not two sparse little nuclei with lots of nothing between them politely drifting past. It's two extended quantum structures, each one filling a real region of space with real charge, meeting and strongly resisting interpenetration. The so-called emptiness is only empty of mass. It is full of field, full of force, full of quantum mechanical structure. Matter resists compression not despite its inner architecture, but because of it. The forces that push back don't require continuous solid stuff between atoms. They arise from the quantum mechanical behavior of particles in space, and they are powerful enough to hold up skyscrapers. So next time someone says atoms are mostly empty space, as though it's an unsettling revelation, remember that the space is not empty. It's occupied by the very forces that make your chair worth sitting in. There's one more dimension to this story worth sitting with, and that's the question of consistency. The rules we've been describing, electromagnetic repulsion, quantum mechanical exclusion, interatomic potential, are not variables. They are not adjustable settings that might happen to be slightly different on a given Tuesday. They are consequences of the fundamental laws of quantum mechanics and electrodynamics, which, as far as physics can determine, apply everywhere in the observable universe, at all times, without exception. This means the ground does not need to check its schedule before holding you up. The wall does not need to remember its job. The electromagnetic force doesn't wear out. Every time you set a glass on a table, the table undergoes a physical interaction that is completely governed by law and arrives at the same answer. The glass stops here, every time, without negotiation. This dependability is not coincidental. It is the actual structure of the physical world. Stars form and persist. Planets don't evaporate. Bones hold their shape. Your body, a staggeringly complex arrangement of roughly 7 octillion atoms, somewhere in the neighborhood of 7 times 10 to the 27th power, maintains its structure from moment to moment, not because it's fighting against chaos, but because the rules at the atomic scale are orderly enough to support enormous complexity. That order extends outward in every direction. The floor holds, not by luck, not by convention, by law. Let's bring this home. You asked at the start, why can't you walk through walls? And we've now traced the answer from everyday experience all the way down to the quantum mechanical structure of matter and back up again. The outermost electrons of the atoms in your body, when brought close to the outermost electrons of the atoms in a wall, interact through the electromagnetic force. That repulsion grows with extraordinary steepness as the distance shrinks, reinforced by quantum mechanical rules that govern how electron states can be packed together. Together, these effects produce what we experience as firmness, as resistance, as the steady push of the world back against us. The wall is not a mystery. It is not an arbitrary limitation. It is the same physics that holds your bones together, keeps water in a glass, allows bridges to stand and mountains to persist across geological time. The forces that stop you at the wall are the same forces that make you possible at all. Here is something worth carrying with you. The next time you press your hand against the table, or lean back in a chair, or walk across a room and feel the floor meeting each step, you are not experiencing an illusion. You are not being misled by your senses into believing in something that isn't there. You are feeling the force of charged quantum structures resisting interpenetration, obeying rules that have not changed since the first atoms formed, expressed through the architecture of matter all the way up to the scale of hands and chairs and rooms. The hardness of the world is not a trick of perception. It runs all the way down. The wall is real, the floor is real, your hand is real, and the forces keeping them distinct, keeping them whole, keeping them and you intact right now are some of the oldest, most carefully understood, and most steadfast phenomena in the history of science. You can't walk through walls because the universe, at its finest grain, has arranged itself in such a way that you don't fall apart either. That seems like a fair trade.